In today's design session, we are going to discuss design for Google Drive. So let's dive in. Now, let's take a moment to understand Google Drive before jumping into the design. Now, Google Drive is a file storage and synchronization service that helps you store documents, photos, videos, and other files in the cloud. You can access your files from any computer, smartphone, or tablet, and you can easily share those files with your family, friends, and coworkers. On the right hand side, you can see a screenshot of Google Drive. Before going any further, let's remind ourselves of the design discussion framework. So as a first step, we should establish the problem statement. Second, we should agree on requirements. That might mean some napkin maths, tendencies and invariants for the solution, system correctness and operational requirements, and discuss in and out of the scope things. Then as a third step, we should outline a high-level design, and then from there on, go into the low-level components. If time permits, we could discuss failure modes, error handling, and then finally, discuss some metrics, experiments, setup, security and durability aspects of the design. So let's establish the design scope here. Important features for the Google Drive would be file sync, file upload, download, and notifications. Now, let's assume all file formats are supported. Storage needs to be encrypted. Files could be 10 GB or smaller, and there's a 10 million daily active users. So to summarize, we should be able to add files, and the easiest way to add a file is to drag and drop a file into Google Drive. Then we should be able to download files. We should sync files across multiple devices. When a file is added to one device, it is automatically synced to other devices. We should see file revisions, then share files with friends, family, or coworkers, and then send a notification when file is edited, deleted, or shared. There are some key non-functional requirements that we should outline. So first is like reliability. Now, reliability is extremely important for a storage system. Data loss is unacceptable. Fast sync speeds. If the sync takes too much time, users will become impatient and abandon the product altogether. Then bandwidth usage. If a product takes a lot of unnecessary network bandwidth, users will be unhappy, especially when they are on a mobile data plan. Scalability. The system should be able to handle high volumes of traffic and high availability. Users should be able to use the system when some servers are offline. Here are some back of the envelope calculations. Again, they are not representative of actual Google Drive, but just some initial numbers to get the discussion going. So we have like 50 million signed up users, 10 million DAU. Users get 10 GB of free space, assuming users upload 2 files per day. The average size would be 500 KB. We're saying 1:1 read to write ratio, which is not really practical. In real world, it will be close to around 7:3 or probably 8:2 or even 9:1. Then total space allocated is 500 petabytes, and the QPS based on these numbers could be around 400 to 500. So let's start with something simple. Let's build everything in a single server and gradually scale it to support millions of users. So let's say we have a web server to upload and download files, a database to keep track of metadata like user data, login info, files info, etc. And then we have a storage system to store files. Now we can allocate 1 terabyte of storage space to store files. There'll be some APIs for sure. So the key APIs could be upload a file to Google Drive. The uploads could be couple of types. One could be like simple upload. Use this upload when the file size is small. Resumable upload. Use this upload type when the file size is large and there is a high chance of network interruption. A resumable upload is achieved by the following 3 steps. Send the initial request to retrieve the resumable URL, upload the data and monitor the upload state, and if upload is disturbed, resume the upload. The second API could be download a file from Google Drive, and third would be get file revisions. Now moving away from single server. So first we'll need some sort of load balancer. So a load balancer distributes network traffic. A load balancer ensures evenly distributed traffic. Then there's a web server. After a load balancer is added, more web servers can be added, removed easily. And then there's a metadata database. And then there's a file storage. You could use S3 or any other cloud storage out there. Then on the right hand side, you can see the figure based on our discussion so far. So the high level the high level diagram looks like, okay, you have a set of users, their request goes through load balancer, API servers, then they talk to metadata DB and file storage. And here's a bit more detailed diagram. So you have a user, load balancer, talks to API, metadata cache, metadata DB, then you have a notification service, and then you have a cloud storage, and then you have cold storage. So all these components we have discussed in prior design, so I'm not going to talk about them, but on a high level, the figure kind of makes sense. So notification service, it's a pub sub system that allows data to be transferred from notification service to clients as certain events happen. In our specific case, notification service notifies relevant clients when a file is added, read, edited, removed elsewhere so that they can pull the latest changes. Then there's an offline backup queue. If a client is offline and cannot pull the latest file changes, the offline backup queue stores the info as changes will be synced when the client is online. Now, for large files, there are which are updated regularly, sending the whole file on each update consumes a lot of bandwidth. So two optimizations are proposed to minimize the amount of network traffic being transmitted. One is delta sync. When a file is modified, only modified blocks are synced instead of the whole file using sync algorithm. Compression. Applying compression on blocks can significantly reduce data size. So blocks are compressed using compression algorithm depending on the file types. In our system, block servers do the heavy lifting work for uploading files. Block servers process files passed from clients by splitting them into blocks, compressing each block and encrypting them. Instead of uploading the whole file to the storage system, only modified blocks are transferred. Now, as you can see, a file is split into smaller blocks. Each block is compressed using compression algorithms. And to ensure security, each block is encrypted before it is sent to the cloud storage. Blocks are uploaded to the cloud storage. High consistency requirements. Now, our system requires strong consistency. By default, it is unacceptable for a file to be shown differently by different clients at the same time. The system needs to provide strong consistency for metadata cache and database layers. Memory caches adopt an eventual consistency model by default, which means different replicas might have different data. To achieve strong consistency, we must ensure the following. Data in cache replicas and the master is consistent. Invalidate caches on database write to ensure cache and database hold the same value. Metadata database. User. The user table contains basic information about the user such as username, email, profile, etc. Device. Device table stores device info. Push ID is used for sending and receiving mobile push notifications. Then there's a namespace, which is the root directory for a user. Then there's a file version, it stores versions history of a file, and block, which stores everything related to a file block. So here is the upload flow. The sequence looks like the sequence for metadata addition looks like, client 1 sends a request to the metadata of the new file. It stores the new metadata in the metadata DB and changes the file upload status to pending. Notify the notification service that a new file is being added. The notification service notifies relevant clients, that is client 2 in this case, that a file is being uploaded. And then looking at the flow for uploading files to cloud storage, client 1 uploads the content of the file to block servers. Block servers chunk the files into blocks, compresses them, encrypts the block, and upload them to the cloud storage. Once the file is uploaded, the cloud storage triggers upload completion callback. The request is sent to API servers. File status is changed to upload in the metadata DB. Notify the notification service that a file status is changed to uploaded, and the notification service notifies relevant clients that a file is fully uploaded. Now the client in this case is client 2. So download flow. A download flow is triggered when the file is added or edited elsewhere. How does a client know if a file is added or edited by another client? There are two ways a client can know. A client A is online when a file is changed by another client. Notification service will inform client A changes are made somewhere, so it needs to pull the latest data. If client A is offline, then a file is changed by another client. Data can be saved to the cache. When the offline client is sent online, it pulls the latest changes. Now, here's the download flow pictorially. The trace we can trace it. So basically, as step 1, notification service informs client 2 that a file is changed somewhere else. Once client 2 knows that the new updates are available, it sends request to fetch metadata. API servers call metadata DB to fetch metadata of the changes. Metadata is returned to the API servers. Client 2 gets the metadata. Once the client receives the metadata, it sends requests to block servers to download blocks. Block servers first download blocks from the cloud storage. Cloud storage returns blocks to the block servers, and client 2 downloads all the new blocks to deconstruct the file. Now, failure handling. Well, all the different components could fail, and then we should discuss, okay, what are the the single point of failures, or what are the the critical path failures that we should avoid. As part of this discussion, we could discuss like load balancer failure, block server failure, cloud storage failure, which is highly unlikely. I mean, if you're building a solution on top of some cloud storage and it fails, yeah, there's nothing much you can do. You can have some redundancy by doing some hybrid solution, but generally the cloud storage providers out there give really good guarantees. API server failure, metadata cache failure, metadata DB failure. So here are some final thoughts. The combination of strong consistency, low network bandwidth, and fast sync make the design interesting. Our design contains 2 flows, managing file metadata and file sync. Notification service is another important component of the system. It uses long polling to keep clients up to date with the file changes. Like any system design interview question, there is no perfect solution. Every company has its own unique constraints, and you must design a system to fit those constraints. Knowing the trade-offs of your design and technology choices are important. If there are a few minutes left, you can talk about your different design choices. For example, you can upload files directly to the cloud storage from the client instead of going through the block servers. The advantage of this approach is it makes the file upload faster because the file only needs to be transferred once to the cloud storage. In our design, a file is transferred to block servers first and then to the cloud storage. And here are some useful references for you to work read on your own. I highly recommend to go through at least a couple of them. My suggestion would be How We Have Scaled Dropbox. It's a really good talk from early engineer at Dropbox. And then I would say differential synchronization, which is pretty neat talk as well. That's all I got. Hope this was useful. Have a nice time. Like, subscribe, and comment for more such designs.